Okay, what is the problem?
Okay, hang on.
Because 18 is the interest rates, right?
Yeah.
So all we had to do is use the two models.
Yeah, I plug everything in. I got like way wrong.
How do you know they're way wrong?
Because
Okay. So
I got like 22,000. I get how that happens when I start with 500.
that would be awesome. Okay, A of t. Yeah, I know. A of t is equal A0 times 1 plus r over n to the nt. Right? Right, so in part A, it asks, so t is equal to 2, right? And it asks annually, which means n is equal to 1. So you're going to have a of 2 just going to be 500 times 1 plus 0.14 to the second power.
Oh, that's fine. I did 1.14 because I thought if it's expanding, you multiply whatever it is by 1.14. And if it's decreasing, 1.5.
This one takes into account your original sum.
Oh, okay.
And so that's why R literally is just a plugging in what is R, and R is 14%, which of course I can't imagine there's a bank that would actually give you 14%, but nonetheless, that'll just be 0.14. Does that make sense? Do I need to do anything else with it?
Wait, so I can just do that for
every single one of them.
Okay. And then
For well, I guess I should call this I. For 2I, you're looking at quarterly, which means n is equal to 4. So it'll be just 500, 1 plus 0.14 over 4 to the 8th power, because it's 4 times 2.
I was surprised at the difference between monthly and daily was only $1.
Yeah?
It can be like a lot more.
I think because at that point n is relatively large. Since you're talking about, well, I guess between 12 and 365. Yeah. As it turns out, the differences aren't going to be that much grand. Even for continuously, you're not going to have that much big of a difference.
for continuously, it's pretty much going to be 0, right? Since you have infinity in the denominator.
What do you mean 0?
Okay.
For continuously,
Yeah.
This is what we talked about last time. For continuous, your model looks like a of t is equal to a0 e to the rt.
That's just what it looks like.
Yes. That's what we discovered considering 1 plus 1 over n to the nth power. As n goes to infinity, that's e. So we did that little trick.
I'm just going to take your word for it.
Okay. I'm glad to hear that you guys are paying attention to what I'm saying. I should give you like a weekly quiz, pop quiz once in a while, just to see how much you actually are paying attention.
You should buy us all coffee if you do that.
I should buy you coffee?
All of it.
Maybe you should buy me coffee. Yes.
Did you do 14? I couldn't figure out.
14 on the same section?
Yeah. I had the hardest time figuring out like how to set it up.
A thermometer is taken from a room when the temperature is 20 degrees to the outdoors,
It was like exactly the same as the
where the temperature is 5 degrees Celsius, right? Okay, so after 1 minute the thermometer reads 12 degrees Celsius. So let's figure out exactly what, this is 14 on page 174. So let's figure out exactly what it says. So a thermometer is taken from a room where the temperature is 20 degrees Celsius to the outdoors where the temperature is 5 degrees Celsius. So would you tell me what T of S is? 5 degrees. Does that make sense? Also, t of 0 is equal to 20 degrees. Right? So now your model is just going to be dt over dt is equal to k times t minus 5. Right? This is what I was telling you when we looked at these types of problems. I said, just write the actual differential equation first, and then work with it from here on. So now, our substitution should just be y of t is equal to t of t minus 5. Does that make sense? This is what I was telling you last time, right? If you make the substitution of the parenthesis, then dt over dt or dy over dt is the same as dt over dt. So this differential equation becomes dy over dt is equal to k times y, which means y of t is just going to be y of 0 e to the kt, right? And let's plug it in. What is y of 0? Well, since t of 0 was equal to 20, and y of t, or y of, well, okay, I guess I don't need to go into that much depth. Y of 0 then is going to be 20 minus 5, so it's equal to 15 degrees. Right? So far so good? So then y of t will just be 15 e to the kt. Right? But this is y, so we have to revert back to t. So from here, t of t will just be 15 e to the kt plus 5. Right? Is this making sense?
Really?
Which part is confusing?
I don't understand how you get for y of t equals t of t minus 1. I can understand the k, the dt over dt equals k of t minus 5.
Okay, so that's the original differential equation, right? If I make this particular substitution, then my original differential equation becomes this. Right? This is how the section began, and we said that this differential equation will have this solution. So all of a sudden I solved it. Now all I have to identify is y of 0, which I do. Right? And now the idea is, I started with t, so I need to revert back to t. So from here, t is just going to be y of t plus 5.
Okay.
Which is y of t plus 5. Does that make sense? Is everybody understanding this? I'm guessing no? Or partially no? So the only trick about these problems, once you figure out the original differential equation, which is this, once you figure the original differential equation out, everything else is literally the same way as we just did problems in the, there's problems in examples and what I did in class, in the sense that you make a substitution for the parenthesis and everything will just follow from basically what we've done before. So if you make the substitution here, okay, do you see that that differential equation turns into this differential equation? Is everybody seeing this? Yes? Since the derivative of 5 is 0, so the derivative of y is the derivative of t times minus the derivative of 5, which is 0. So the derivative of y is the derivative of t, right? So the left hand side is that, and the right hand side we make a substitution t minus 5 to be y. So I'm just writing it out. So far so good?
capital T the same as T of T?
Yes. Yeah, in differential equations it's standard that you don't actually write the variable. But yeah, here it would be T of T and here would be Y of T. Okay? So far so good? Okay, now this has a solution of this nature. That's what we talked about in the section, that's what we discovered that, that's the case. So from here to here is just literally what we've learned. So once I get here, from here on, it's nothing else but algebra. That's it. Right? I have to replace whatever y0 is with whatever number that is. I'm going to have to revert back to t's because that's what I started with. Now clearly I'm not actually done. Why? Well, I still don't know what k is, right? The only thing I've done is, if you remember the original problems when I looked at the exponential growth and exponential decay, I said here's the function, now let's figure out what the initial value is and what k is, right? So far the only thing we've done is, this is our equation, this is our initial value, let's figure out what k is. So this is where the fact that after 1 minute is 12 degrees is where you figure out what k is. Does that make sense? Everybody understands how to get that? Clearly, by the way, this is what I was telling you last time. You have to read the problems and figure out what your units should be. And clearly, since we're talking about minutes, the time should actually be in terms of minutes, not hours, right? Since you don't really want to deal with 1 over 60 or 2 over 60 or, something along those lines. So, t of 1 then is equal to 15 e to the k plus 5, and we know that's equal to 12. So, e to the k is just going to be 7 over 15. So k is natural logarithm of 7 over 15. And this is what I was saying when we looked at these problems. What should I expect? Well, I should expect k to be negative, right? And it is negative because 7/15 is less than 1. Why should it be negative? Well, because clearly we're looking at a decay, right? We started with 20 degrees and after 1 minute we're already down to 12, right? Does that make sense? So, would you know how to answer it? What is it asking you? What will the reading on the thermometer be after 1 more minute? T of 2, right? We already figured out what k is, so all you have to do is just plug in 2 in for t, right? Does that make sense? And as the last question says, when will the thermometer read 6 degrees? So we need to find t, right? So find t when t of t is equal to 6. Right? Does that make sense? This is a very rapid decrease. So I would anticipate that it'll read 6 quite fast. I don't know if anybody actually solved it, but I would probably say less than 5 minutes. Right? Since in 1 minute it already lost 8 degrees. Okay? Yes?
Okay, I'm stuck on 18b.
18b. Okay, why are you stuck on 18b?
Okay.
Oh, you're not supposed to do 18b.
I'm not?
No.
Did you say not to? Oh, okay.
I forgot to actually write it on the homework sheet, and I don't remember if I said it verbally or not. But 18b, it's usually my general rule. If it's anything involving with graphing, I'm not going to ask you to do it, since I don't necessarily. I would have to actually force you to have a graphing calculator or to have some graphing tools. So If you did it, I guess you learned something extra. 3-5, number 6. Kelly?
Are we going to have word problems on next Wednesday's test?
Word problems?
Yeah.
By all means, of course.
So I should memorize like the interest one. I should memorize.
3-5 will not be on the test. Oh, sorry, 3-4 will not be on the test. The whole section 3.4 will not be on the test, yes. You've seen exponential growth and decay before. I just wanted to kind of give you a perspective on how things work. You played with homework long enough, so you don't have to worry about that anymore. And besides, if you are actually like math majors, or if you're actually planning on taking more math courses, you're going to see a lot more differential equations later on. So, this is just going to be like an introduction. Yes.
Did you say you're not going to make a study guide for this exam?
When did I say that?
You said you weren't going to do that anymore after last exam.
Is that what I said?
You said something like, I'm not going to make a cheat sheet anymore.
No, actually, I was hoping to bring you the outline today, and I did not get a chance to actually finish it. So I will probably have it on the website sometime this afternoon. So if you want to actually get ahead on things, get a head start on things and get, start working on it, you can do that. If not, I'll for sure bring everybody a copy on Friday. So, but it will be on the website probably sometime this afternoon. If not, tomorrow morning at the latest.
And then will the solutions be put up over the weekend?
Yes. Oh man, I gotta write solutions now, huh? That's the danger of assigning, giving you extra stuff. I have to work extra. Number
3-5,
number 6.
Part B.
Part B? Ah, that's a good one. Cosine of 2 times sine inverse of 5/13. So how do we solve this? Obviously, you can probably put in a calculator and come up with some sort of a value, but you tried?
I didn't like 5/13 that's the inverse.
Okay. Well, how should we approach it? Well, with all of these types of problems, the way we approached things is we let theta be sine inverse of 5/13.
Yeah.
Right? So from here, sine of theta is equal to 5/13. If you draw a lovely triangle, what do we know? The opposite is 5, the hypotenuse is 13, which means the adjacent is 12. Pythagorean numbers, 5, 12, 13. If not, obviously, do I need to explain where I got the 12? Pythagorean theorem, 13 squared minus 5 squared is 144. Okay? So, what do we do next?
Do you increase the entire triangle?
No. Cosine of 2 theta. So we're looking at cosine of 2 theta, right? And this is where your knowledge of trigonometry from pre-calculus is going to surface up and say, what is the double angle formulas? Well, that's just cosine squared of theta minus sine squared of theta. Did it surface up now? Do you remember actually seeing this? Vaguely? Okay. So using double angle formulas, you can have that. And now it's just basically just plug and play. 12 over 13 squared minus 5 over 13 squared. So what is that? 19. So 119 over 169. Yes.
So you don't actually find the theta?
No, we never do. We never, with all of these inverse functions, you never really find theta. Because, I mean, obviously in this situation, you could technically plug in sine inverse of 5/13. You know, you can take out a calculator or a computer or something and actually compute what it is. But what happens if I actually would just put x in for 5 over 13? Then you wouldn't actually be able to figure out what it is. Sure. Is this making sense? Yes?
Yes.
Okay. Well, A is very similar. You have secant of tangent inverse of 2. So, again, if you let theta be tangent inverse of 2, then tangent of theta is equal to 2. We draw a lovely triangle. If this is theta, what do we know? The opposite 2, the adjacent is 1, which means the hypotenuse is the square root of 5. Do you understand what I'm getting these numbers, by the way? Because I always kind of skip over the Pythagorean theorem, but I want to make sure you understand how to get them. Is everybody understanding how to get them? Okay? And so from here, we're looking at secant of tangent inverse of 2. Well, that's just secant of theta, which will be square root of 5 over 1. So it's just the square root of 5. Does that make sense? Number 30 on 3.3. Okay, so y is equal to e to the u minus e to the minus u divided by e to the u plus e to the minus u. Now today, we're actually going to find out that y is equal to the hyperbolic tangent of u. Which, when we take the derivatives, it'll actually be secant squared, hyperbolic secant squared of u. Now, if we don't know that, which we don't, dy over du is equal to e to the u plus e to the minus u times e to the u plus e to the minus u minus e to the u minus e to the minus u times e to the u minus e to the minus u, all divided by e to the u plus e to the minus u quantity squared. And it is at this point where we actually say, let's simplify. And as it turns out, it simplifies very nicely. Do you want the long version or do you want the short version?
Short? Actually, no. We're going to be learning the short version.
The short version is just that the numerator is 4. So I'm guessing the long. We have e to the 2u plus 2 times. Can you tell me what e to the minus u times e to the u is? Just 1, right? So we just get 2. Plus e to the minus 2u minus e to the 2u minus 2 plus e to the minus 2u, all divided by e to the u plus e to the minus u quantity squared. Notice that all these cancel out and you're left with 4 over e to the u plus e to the minus u quantity squared. I did a semi-long version. Yes.
Boy, I'm still not understanding how you get 2.
Well, what is
U times e to the minus u?
what is e to the u times e to the minus u?
Isn't that either 0?
Which is?
E to 0 is 1.
Okay.
Oh, you do that several times. Okay, I got it.
Is this making sense? Yeah? Okay. Anything else? I guess we've been at it for half an hour. Yes.
56 on 3.3, or 58 on 3.3.
58 on 3.3.
X to the Y equals Y to the X.
Ah. That's a good one.
Yeah, that's right.
As it turns out, it's not bad. It just looks funny. So the only way to solve this particular derivative is to apply ln's both sides. So basically use logarithmic differentiation. There are problems that the only way you can solve them is using logarithmic differentiation. Same one for 50, 52, 54. Those are all required to use logarithmic differentiation. You can't do them any other way, right? Because technically you're looking at a function to a function. So if you apply ln both sides, this is long or short? ln of x to the y equals ln of y to the x, which says y, we use the butterfly effect. Y ln of x equals x ln of y. And now if you take derivatives both sides with respect to x, what do we get on the left hand side? dy dx times ln of x plus y times 1 over x equals ln of y plus 1 over y dy dx times x. Everybody follows? Based on the amount of people writing it out, I'm guessing that's not what you were actually doing. Is this making sense? Again, well, there's two things here that you have to take into account. First of all, logarithmic differentiation. Second of all, this is implicit differentiation for all of them, right? And then both sides actually are products of two functions, so you have to apply the product rule both sides. Okay? Can you solve for dy over dx here?
Yeah.
Yes? Wonderful. Okay, what else?
36 on 3.5.
36 on 3.5? Pi over 3. So the idea is you have the limit as x goes to infinity of arc cosine of fraction 1 plus x squared divided by 1 plus 2x squared. And the idea is that arc cosine is a continuously strictly increasing function. So it's a function that behaves nicely, which means I can interchange the arc cosine and the limit. And now what is the limit of 1 plus x squared over 1 plus 2x squared? It's a polynomial over a polynomial, so we can talk about the ratio of the highest power, since they have the same powers. So it'll just be 1 over 2. right? If not, factor out x squared, cancel them out, and work out the algebra that way. The idea is you end up with arc cosine of 1/2. And the question is, cosine of what angle is 1/2? And the answer is pi over 3. Does that make sense? Okay. Anything else? 56 on 3-3. Okay. So you have x e to the y plus y e to the x is equal to 1. So we need to apply we need to apply implicit differentiation to get dy over dx, right? So when you take derivatives both sides, we end up with e to the y plus x e to the y dy dx plus dy dx e to the x plus y e to the x is equal to 0. Does that make sense? Do you understand where this is coming from? Again, the whole point of me answering questions for the homework is not so you can get 2 extra points or 3 extra points for the homework, is for you to actually understand the concepts. So if you're not understanding this, I'd much rather actually spend 2 minutes explaining it rather than just giving you the answer and moving on. Yes?
Okay, so what was the equation?
I'm not done yet.
Oh,
I'm just asking if you understand the derivative. Is everybody understanding the derivative? Implicit differentiation. Take derivatives both sides with respect to x. Obviously the right hand side is 0, so we don't have to worry about that. Product of functions. X times e to the y. Derivative of the first times the second, plus the derivative of the second, which is e to the y. The derivative of e to the y is just e to the y times y prime, times x. Plus, move on to the next one. Again, I have a function of x and a function of x. Product rule, derivative of the first times the second, so it's just the derivative of y times e to the x, plus the derivative of e to the x, which is e to the x, times y, which is the last term. Okay? Now, of course, I can solve for dy over dx, but I figure what's the point? Since we can make our life a lot easier, plug in the 0.01. Why? Because some things will cancel out. Whenever you see x, there's just going to be 0. So for instance, the second term is x times whatever stuff. I don't care because it's 0 times whatever that is. Right? So I'm going to have e to the 1, so e, plus 0, plus dy over dx, times e to the 0, plus 1 times e to the 0 is equal to 0. Right? So I just have e plus dy dx plus 1 is equal to 0. So dy dx is going to be minus e minus 1. So your equation is just going to be y minus 1 equals minus e minus 1 times x minus 0. Again, remember, parentheses are your friends. That's what I've been trying to tell you all along. Make sure you put parentheses here, because if you don't, then the assumption is that it's just going to be 1 times x. Right? But this is the actual slope, so that gets multiplied by x minus 0. Okay? Yes? Mm-hmm.
Something raised to something else.
Mm-hmm.
How do you take it?
Logarithmic differentiation. The only way to do it is to apply ln's both sides and take implicit differentiation. So y equals x to the cosine of x. As a first step, you say ln of y is equal to cosine of x times ln of x. Using the coined phrase by now, butterfly effect. And now you just do implicit differentiation in both sides. 54. If you have a function to raise to another function, the only way you can do this is actually applying ln both sides. There's no other way you can actually attack the derivative. Patrick?
Could you show how to properly apply the chain rules we have in
36 on 3.3? I didn't do that problem in class? I must have done it in the other section. Y equals 2 to the 3 to the x squared. So what do we notice here? We have 2 raised to stuff, and the stuff is actually 3 raised to stuff, right? So we're going to actually end up having 3 chain rules, right? So what is the derivative of 2 to stuff? It's 2 to stuff times ln of 2 times the derivative of the stuff, right? Nah. It's 3 to the x power x squared. It's not 3 times x squared. Bless you. So I have to take the derivative of 3 to the x squared. So again, now what is the derivative of 3 to stuff? Different stuff now. 3 to stuff times natural log of 3 times the derivative of the stuff, which is 2x. Does this make sense?
Which rule says that we need to repeat the first, the text?
Well, technically, you have 2. This is why I keep calling it stuff, because it's easier to just notice. Just think about it as a black box. You don't necessarily know what's in it, right? That's actually how chain rule works. So I have 2 to some function. So when I take the derivative, it's just going to be 2 to that function. Oh, sorry. I have 2 to that function, right? So it's going to be 2 to that function times ln of 2 times the derivative of that function. So now when I look at that function, right, I open up my black box and I look inside it, I have 3 to some other function. So I have to apply basically the chain rule to the inside function. So now I have 3 to some function. What's the derivative? Well, it's going to be 3 to the function times ln of 3 times the derivative of the function. Does this make sense? So just for fun, I should probably maybe put this in a test. X to the x to the x? Nope. The only way you can solve it is actually logarithmic differentiation. So you have to apply ln both sides, but you actually have to apply ln both sides twice. So it'll be ln of y is equal to ln of x plus x ln of x. And then you take derivatives and have fun with that. Okay. Are we finally done?
Yeah.
Okay. So let me collect it before I forget. Anybody else came while I was... Jenny. Okay. Thank you.
Because we have one for the entire
Okay, so today we're going to talk about trigonometric hyperbolic functions. And I'm not going to spend a lot of time on this. So originally, what I was planning on doing, but that might not necessarily be the case, considering it's 10:10 already. Well, I was actually going to go through 3.6 relatively quickly, and then probably start 3.7, because there's a lot of finesse things in 3.7 that I want you to actually get. But anyway, here's the idea. Hyperbolic trigonometric functions are defined the following. Sinh of x is defined to be e to the x minus e to the minus x over 2. And cosh of x is defined to be e to the x plus e to the minus x over 2. Okay? Now, if you are to actually graph the functions, it turns out we can graph them relatively easily. Why? If this is the graph of y equals minus 1/2 e to the minus x, and this is the graph of 1/2 e to the x, do you see where I'm getting these values from? Think about dividing this, separating this into two fractions. Those are going to be your two values, right? Then the graph of sinh of x is nothing else but how did I get all the way up there? We don't know. But anyway, it's going to be that graph. I drew it very badly. It's actually, your textbook has it much better graphed. The idea is, as x goes to minus infinity, your graph, you will actually be very close to this graph. Why? Because at minus infinity, e to the x is 0. So you're only going to end up with the second term. When x goes to infinity, this quantity is 0, and so your function is actually going to behave like 1/2 e to the x. Is that making sense? Okay, similarly for cosine of x, for cosh of x, this is the graph of y equals 1/2 e to the minus x. This is the graph of y equals 1/2 e to the x. And on the exact same token, your function is going to behave like that. Okay? Now, what is tangent of x? So the hyperbolic tangent, well, as it turns out, it behaves exactly the same as the regular tangent. It's just sine over cosine. In this case, it would be sinh over cosh. So you just end up with e to the x minus e to the minus x divided by e to the x plus e to the minus x. Does that make sense? So far, so good? Okay. Now, you might ask yourselves, why in the world are we calling them hyperbolic trigonometric functions? Because if you look at the way they're defined, they're just exponential functions, right? So why would you actually define them to be hyperbolic? And as it turns out, the reasoning is actually quite simple. Can you tell me what, let's see, cosh squared of x minus sinh squared of x might be? it ends up being equal to 1. Do you want to see why? Well, it's actually just algebra. You get e to the x plus e to the minus x squared divided by 2 minus divided by 4, so 2 squared, minus e to the x minus e to the minus x squared divided by 4. And I'm going to skip the details because I actually just did this about 15-20 minutes ago. This is just 4 over 4, so it's equal to 1. Remember when we took the derivative of the hyperbolic tangent? Even though it wasn't defined that, you know, the e to the u's? This was the numerator. Remember? And we just worked it out, and you saw that it was actually equal to 4. So it'll be 4 over 4 equals to 1, right? Well, this is actually the key idea. Cos squared of x minus sinh squared of x is equal to 1. Now, if you remember, cosine squared of x plus sine squared of x is equal to 1 is the fundamental trigonometric identity, because you're related everything to a circle, right? Any point on the circle has coordinates. Do you remember this? What are the coordinates? Since you remember? Keep in mind, again, if you don't remember what they are, and I said this in the class a few times, and you don't necessarily have to do this, but I personally do that all the time. I don't remember sometimes if it's cosine of x and sine of x, or sine of x and cosine of x, but it's very simple to remember. What's sine of 0? Sine of 0 is 0, right? So if you look there, this point here has coordinates 1 and 0, right? Which means this has to be cosine of x, sine of x. Does that make sense? Do you remember why? Okay, cosine always goes first, alright? Okay, now, the reason why we call them hyperbolic trigonometric functions is because any point here will have coordinates cos of x and sinh of x. Why? Because x squared minus y squared is equal to 1 is the equation of a hyperbola. Which I probably should have started off with that, because how many of you remember the equation of a hyperbola?
No.
Do you remember the equation of an ellipse?
Yeah, it's like y squared plus x squared equals something squared.
Nope. If you have a minus between them, then it's a hyperbola. This minus tells me that my asymptotes look like this. Or if you want them, if you want to call them parentheses or however you want to call them. If you would be y squared minus x squared, it'll look like this. An ellipse is just x squared over a squared plus y squared over b squared is equal to 1. Okay. So this is more or less the reasoning behind hyperbolic equations. Now, can you tell me what the derivative of cos of x is? Just take the derivative. What is the derivative of e to the x plus e to the minus x over 2? Well, it's going to be e to the x minus e to the minus x over 2, which ends up being sinh of x. Yes?
Why does the minus sign change?
Well, what's the derivative of e to the minus x?
Oh, okay.
E to the minus x times negative 1. right?
Yes.
Is this making sense? 2 is a constant. So we're only taking the derivative of the numerator, right? It's the same thing as what's the derivative of x over 2? Well, it's just 1 over 2 because 2 is constant, it doesn't change. Right? Is this making sense? Okay. What is the derivative of sinh of x? Well, after some elaborate mathematics, it ends up being cosh of x. And when I'm saying elaborate, I'm being ironic because all you have to do is just, or sarcastic, all you have to do is just think about the derivative of this. You'll have e to the x minus e to the minus x times minus 1, so that makes it a plus, which brings it back to cosh. What is the derivative of tanh of x? Sech squared of x, which is the hyperbolic secant squared. Remember from the problem we did in the homework, it was 4 over e to the x plus e to the minus x quantity squared, right? But that's just 1 over cosh of x squared, right? Yes? Remember, when we took the derivative of e to the x minus e to the minus x divided by e to the x plus e to the minus x, we ended up with 4 over e to the x plus e to the minus x quantity squared. But this is just 2 over e to the x plus e to the minus x squared. So it's just 1 over cosh of x squared. Okay? Does this make sense? Okay, so now this is where I'm basically kind of ignoring the second part of the section. I can tell them to you if you want, but I don't know them in general. I actually would have to look them up because they never really get used that much. But the second part of the section deals with inverse hyperbolic trigonometric functions. So we're looking at cosh inverse of x, sinh inverse of x, and so forth. Well, as it turns out, so cosh inverse of x is equal to y is equivalent to saying cosh of y is equal to x, right? Now, if you remember the graph of cosh is always positive, and it looks like a U, right? Which means it's not 1-to-1. We have to restrict y to be only positive, right? This is the graph of cosh, the orange line. So you have to restrict it to be 1-to-1. So you have to restrict it on the positive side, right? So anyway, here we would have to say that y has to be bigger than or equal to 0. But now, as it turns out, cosh inverse of x can actually be computed. And it's actually the natural logarithm of x plus the square root of x squared minus 1. Do you want to know why?
Yeah.
Yeah?
If we absolutely have to get
You absolutely don't have to. I don't know them. I basically looked it up in the book right now. How do you come up with it? Very simple. Cosh inverse of x is equal to y is equivalent to saying x is equal to cosh of y. So then x is equal to e to the y plus e to the minus y over 2, right? Multiply by 2, combine all the terms alike, you'll end up with e to the y minus 2x plus e to the minus y is equal to 0. And the goal is to solve for y, right? That's the ultimate goal. So how do we do that? Well, the problem is we have two exponentials and we need to figure out how to deal with them. But as it turns out, the answer is very simple. Why? Multiply by e to the y both sides. What do you get on the left-hand side? Yes?
Where did the e to the y minus 2x plus e to the negative y come from?
I have that equation. If I multiply by 2 both sides,
Oh, wait, so you have x, which is e to the y plus e to the y, equals cosh of y. You wrote out cosh of y.
yes.
Okay, so it's an equation.
Uh-huh. So far so good? Yes? What happens if you multiply by e to the y both sides? You end up with e to the y quantity squared. I'll write it in this fashion so you actually see where it's coming from. Minus 2x e to the y plus 1 is equal to 0. Right? Pre-calculus, long time ago. How do you solve equations of this nature? X is a constant. Or it's not a constant, but x is not actually what we're looking at. We're looking after y, right? So the way we solve these types of equations, we make a substitution. We let u equals e to the y. And so you end up with u squared minus 2x u plus 1 is equal to 0. And that looks like a quadratic function in u. So u is equal to 2x plus or minus the square root of 4x squared minus 4 divided by 2. You can factor out a 2. Notice you can factor out a 4 under the square root. That can come out of the square root. So this just is x plus or minus the square root of x squared minus 1. Right? So far so good? Now that means that e to the y is x plus or minus the square root of x squared minus 1. And since the left-hand side is an exponential function, it can never be negative. And so as a consequence, we can't take the negative side of it, so we have to take the positive. So when you take the positive, then what you end up with is y is the natural logarithm of x plus the square root of x squared minus 1. Which is exactly how we said that cosh inverse of x is. Anyway, I'm not going to force you to know these. I don't know them. I don't ever expect to know them.
This kind of stuff isn't really going to be on the test.
No, the only thing that I expect out of you from section 3.6 for you to know is what is cosh of x, sinh of x, tanh of x, and what their derivatives look like. That's it. Why? Because personally, those are the only functions that actually show up a lot more. And you might actually ask yourselves, why exactly are we even looking at these types of functions? And as it turns out, they actually have many real applications. What I usually do when I teach this particular section is I read this. But anyway, you can find it on page 181. A catenary. Applications of hyperbolic functions to science and engineering occur whenever an entity such as light, velocity, electricity, or radioactivity is gradually absorbed or extinguished, for the decay can be represented by hyperbolic functions. The most famous application is the use of hyperbolic cosine to describe the shape of a hanging wire. So if you think about it, if you go outside and look out your window, you'll see a lot of electricity, power lines, and you'll see basically the shapes. That's basically, you can model those shapes using hyperbolic cosines. And the reason why you want to be able to model them is, I'm assuming it's quite obvious, right? If you've modeled them, you can figure out what the tension is, what the weight, how close they have to be apart from each other, how much you can stretch them, and all these kind of ideas, right? Which is what people actually do in real life, because chances are, maybe 150 years ago, they just put them up hoping that they work. But now that there's all these Yeah, there's a lot of computer modeling and computer simulation before anybody does anything. Because why are you going to go out and spend a lot of money to build something when it may or may not actually work? So anyway, this is kind of to give you a perspective on things. So you're going to have homework. You have two things. First of all, you need to figure out some numerical values for the expressions, and basically, for the most part, you're going to have the formulas. Obviously, you can look at the formulas when you do the homework. Like, for instance, what's sinh inverse of 1? Well, there's a table, there's a formula that sinh inverse of x is ln of x plus the square root of x squared plus 1. Plug in 1 and see what it is. Obviously, otherwise, you can actually take the inverse of it. But anyway, and then you have to look at some derivatives. Should I do any derivatives? Okay. So, Section 3.7, yes.
So I'm looking at the homework problem, 6. It looks like we're going to be going over the derivative of the inverse. I said you wanted to do that.
I said it's not going to be on the test.
We learned what the derivative of cosh was, but what about sinh? Do we do that?
Yes. I said it verbally that it's cosh.
Inverse.
Well, this is cosh inverse. What is its derivative? 1 over that stuff times the derivative of the stuff. Right?
Yep.
So, there you go.
But what about same thing?
Yes. Actually, there's a table on page 184. It's table 6, or I guess formula 6, that give you the derivatives of all the inverse hyperbolics.
Oh, okay.
So I figured I'm not going to spend the time to go over them. I'm sure everybody can look at the table and figure out what the derivative is just by plugging it in. Is that making sense? I mean, I'm not spending any time on this because I'm not going to test you on this. You're basically getting tested for homework as far as, can I look at the table and plug in the values? I'm sure. I'm hoping you can do that. Does that make sense? Do you want me to do one? Okay. All right. So I'm going to start talking about L'Hopital's rule. The hospital's rule, yes. But the guy was French, so L'Hopital is the way you actually say it. The idea behind it is, this whole section deals with nothing else but limits, okay? And for the most part, it'll deal with limits that we actually don't know how to deal with. So for instance, the limit as x goes to 0 of the natural logarithm of x divided by x minus 1. Well, what happens if I put in 0 for x? Sorry, I don't want to go to 0 because to 0 doesn't make any sense. I need to go to 1. So what happens when I put in 1 for x? ln of 1 is 0. Denominator is 0. I get 0 over 0. Right? This is one of those things that I kept mentioning. Today we're actually going to start talking about what they actually are called. This is called an indeterminate form because it's 0 over 0. The question is the 0 in the denominator winning or is the 0 in the numerator winning? Because if the 0 in the numerator wins, then you end up with 0, right? Because 0 over something, non-zero is 0. And if the denominator wins, you divide by 0, which means you end up with infinity, right? Does that make sense? So the question is, which of the answers is it? Or is it a third answer which says they actually both go to 0 pretty much in the same time, so you end up with actually a finite number? Okay? Now in the past, whenever we had something like this, whenever we had 0 over 0, the first thing that we usually said is, well, clearly we have to be able to factor something out, right? That's what we did. We factor out some sort of a 0, canceled it out, and then we were able to put in the limit. Well, there's nothing I can factor on the top. It's just ln of x that you can't be factored, right? Is that making sense? So the question is, what should we do? And the answer is, L'Hopital came up with the idea. So here's the idea. Suppose f and g are differentiable and g prime of x is not equal to 0 near a. Suppose the limit as x goes to a of f of x is equal to 0 and the limit as x goes to a of g of x is equal to 0, or that the limit as x goes to a of f of x is equal to plus or minus infinity, and the limit as x goes to a of g of x is equal to plus or minus infinity. Then the limit as x goes to a of f of x divided by g of x is equal to the limit as x goes to a of f prime of x divided by g prime of x. Okay? Now, I underlined it, but maybe I should put it in red or orange or whatever this color is. This has to hold in the same time, which means this only works if I'm looking at 0 over 0 or infinity over infinity. Okay? It doesn't work if it's 0 over infinity or infinity over 0. Do you understand that? Yes? Yes?
How is positive infinity over negative?
It doesn't matter the signs. It has to be 0 over 0 or infinity over infinity. So now if I come back to the limit as x goes to 1 of ln of x divided by x minus 1, this is what I would like you to get used to doing, because we're going to do a bunch of these, and we want to figure out that I want to figure out that you know what case you're in, because we're going to deal with a lot of these. By the way, these are called undetermined forms. And we'll find out a lot more of these undetermined forms as we move forward. So this limit is a case of 0 over 0. And I would like you to get into a habit of recognizing what situation you're in and writing it out. And so I can apply L'Hopital's rule. So by applying L'Hopital's rule gives me the limit as x goes to 1 of 1 over x divided by 1, which equals the limit as x goes to 1 of 1 over x, which equals 1 over 1, which equals 1. Does this make sense? Yeah? Now, what is the limit as x goes to infinity of 2x squared minus 5 divided by x squared plus x? 2. Well, if we go back to what we know from the past, factor out an x squared, or just think about the fact that they have the same power, and so you end up with the ratio of the coefficients, right? Now, what happens if you put in infinity for x? We end up with infinity divided by infinity, right? So this is a case of infinity over infinity, right? I can apply L'Hopital's rule, and it gives me the limit as x goes to infinity of 4x divided by 2x plus 1. Right? What now? What is the limit? Well, again, if I plug in infinity, I'll end up with infinity over infinity. Right? Well, if it works once, who's to say I can't really reapply it? So if I apply it again, it'll just give me the limit as x goes to infinity of 4 over 2, which equals to 2. Right? As it turns out, with this particular method, as long as you're looking at 0 over 0 or infinity, you can solve pretty much every single one of these limits that you more or less didn't know in the past. So for instance, the limit as x goes to 0 of sine of x over x. We know this limit is equal to 1, right? I never actually proved this to you. When we looked at this, there was this geometrical proof that I could show you why this limit is actually in fact equal to 1. But I figured, what's the point of spending that time? Because if we use L'Hopital's rule, this is going to come out instantly. Why? Put in 0, you get 0 over 0, right? So we're in a situation of 0 over 0. I can apply L'Hopital's rule. It will give me the limit as x goes to 0 of cosine of x over 1. Cosine of 0 is 1, so I end up with 1 over 1, which equals 1. Does that make sense? You probably don't realize this, but this pretty much saves you from all the limits that you didn't necessarily know what to do with. This is just scratching the surface. We're going to deal with a lot of these on Friday. There's going to be a lot of other undetermined forms that we're going to have to deal with.